right. So welcome back, everybody. Happy Monday to you. I had a good weekend. I was all by myself this weekend for the first time in 2.5 years. Daddy took Huey to visit his family, and I was alone for 3 days. Oh my goodness. It was so exciting, but now we're back. Back to business, back to work, and so forth. I got a chance to look over your quizzes, and if I had anything to say, I went ahead and gave you feedback. If I didn't say anything, you can assume that it was fine. So we still have some folks confusing level 1 and level 2. That's understandable. Getting the words that go together is the main point here. We're going to review more of that today. Homework 3 is out, and you can do maybe the first third to the first half of it. After today, you should be able to do much more, if not the whole thing. If you're willing to wade through chapter 4, you can do all of it, because it's all in there, but we haven't had a chance to talk about all of it yet. So any questions or anything you want to talk about before we dive in? Got some new stuff for today? All right, then we shall dive in. If you haven't already done so, please pull up Lecture 4 and Example 4. While you're doing that, I will point out some resources that you may or may not have known about. So this is the website for my book. It's linked from our course page. After I finished the book manuscript, I spent a year building this website. It has every single model that I talk about at any point in the book in 4 different programs. So if you are somebody, for instance, I spoke with Maddie earlier today, there she is, she's been working in SPSS because she's more familiar with SPSS. Fine. You will find that the code between SAS and SPSS is remarkably similar, and so you can go to your SPSS column and download examples in your program of choice. I have the data, the syntax, and the output for all 4 of these programs. M+ is the only one that looks dramatically different in terms of its structure. But SPSS, SAS, and Stata all have a similar structure to how their programs look for mixed models. Also in the top row here, you will see a general guide about syntax. Rather than annotate every single line of my code, I decided to do it once and do it in English. So for instance, if you're somebody who is trying to remember what the repeated line does in SAS, you can pull up this SAS guide, which talks about how to get your data in and make new variables, and then we get to the proc mix section. And here I tell you what all of the options that I use in my examples do, and try to explain how they work. So for instance, if I can't remember what repeated looks like, you can come down here until you see the word repeated. Keep scrolling, lots and lots of stuff here. That was a bad example. Apparently it's the last one. Yeah, there's random. Yeah, there's repeated. So you can see how to specify everything. So if you're not sure how to do something in SAS, this is a good place to come to look, as well as the other programs. I also posted on our class website one more file that went with example 3B. Let's find that. Here it is. An example of how to do likelihood ratio tests in Excel. We'll be talking about that first thing today, so I will go over that. This is what you have to do if you want to use a program that doesn't do it for you. So Stata has a built-in thing called LR test to do this. SPSS has nothing built in. SAS has nothing built in, but I made a little macro to do it for you. But you can always type in numbers in Excel and do it yourself, so I'll show you how to do that in just a little bit. All right. Questions on any of that? All right, so today, Alternative Covariance Structures is where we're starting off Lecture 4. I am not going to hit all of these slides. Some of these are here just for informational purposes only. I got to be honest with you, this is like the worst chapter in the book to me. It was terrible to read. I bored myself writing it and reading it over and over again. This material is not fun. I'm just going to put it out there. Lots of this stuff is really fun, but this one isn't. But it's one of those things that you have to do to get to the good stuff. So I may have used this analogy before, but it bears repeating. How many of you have had the misfortune to try and paint a room in your home or apartment? Lots of people, okay. So you would think that based on watching commercials at Home Depot, you just go to Home Depot, you pick out your paint, and then you just show up and like your room is done 3 hours later, right? No. No, you have to go and fill in holes, take out all the nails, you have to sand, you have to tape everything off. And if you're a terrible painter like I am, I over tape everything so that I don't slop it all over. You got to drape the floor. You got to do all this extra stuff. You got to take off all the outlets and all the switches. And then you put on the primer and you hope it's good enough. And then you put on the paint, and somewhere between 1 to 4 coats later, it looks like it's supposed to. It's not just about the paint. What makes a good paint job is all the prep work that goes into it. An analogy, of course, nail polish. You can't just slap on nail polish and have a decent looking manicure. There's all this prep work that goes into it. You have to file and buff and trim your cuticles, and it's a whole thing. So you can think of this process like that. This is the priming, taping off, taking off the outlets. It's the part of painting that is no fun, but if you want a good paint job, you got to do it. Similarly, if you want results that you can trust because you did your due diligence at this step, that's what this step is for. So it's not ever going to be fun. No one ever rolled out of bed in the morning thinking, I wonder if I have a Toeplitz matrix or a Toeplitz heterogeneous. No, said no one ever, right? That's never a research question. But it is important to answer the research questions that you do have, that you get the right model for the variance. So that's what we're talking about. Alternative models for the variance, specifically in the context of what I would call fluctuation data. That's where we're at. So these are the daily diary studies, the ecological momentary assessment studies, longitudinal studies where you're trying to gather a lot of data to watch within-person process, not necessarily within-person change. So things like stress or mood or emotion or activity, these are things that show some pattern of fluctuation. Maybe it's a time of day thing, maybe it's a day of the week thing, or maybe it's just random, but it's fluctuation within persons, not change. So I have a picture here up on the right that shows the type of data that this would look like graphically. So we're stopping by that type of data first, and then we'll get to within-person change in the next chapter. So what that means in terms of time, for the model for the means, time isn't going to be necessary in our first example, and it may not be necessary. If you don't have systematic change, if people aren't heading up and down or one or the other, you don't need to have fixed effects of time. Fixed effects of time predict change on average. If you don't have that, you may not need any terms for time in the model for the means. But we do still have to worry about the model for the variance, and that's what this is focused on. So what you know right now are 2 different models for the variance. These are the 2 types of repeated measures ANOVAs. So I'm foregoing the between-person E-only model because it's never plausible that occasions from the same person wouldn't have some relationship. We're just going to get rid of that one for now as a possibility. These 2 up here represent the benchmarks for what are plausible in terms of longitudinal models for the variance. Can you see my mouse on here? It works now. I don't know what I did, but it works now. Hooray. So this one, compound symmetry, that idea is the 2-pile model. So you know this under a variety of names. If it's being estimated with least squares, people would call that repeated measures ANOVA. That's the univariate version. That's the version most people think of when they think of repeated measures. You know this also as random intercept. So it's 2 piles, the idea that at each occasion, so this picture would hold if I had 4 occasions, the variance is shown on the diagonal here. So the first cell is the variance at time 1, second cell is variance at time 2, 3, and 4. This model says that the variance at each occasion is partly because of random intercept, partly because of residual. So let's unpack that sentence. I'm going to write on the board here, but I'll talk aloud as I'm writing. So when I say partly because of random intercept, which of those symbols am I talking about? You can tell me which letter if you don't know the Greek letters. Is that a U or an E? Random intercept. That's the U. Thank you. I like the, is that like touchdown U or something? No? Mm. So that is tau, no, that's a sigma. I hate Greek. We're going to write it out. Tau squared, and I need a damn marker. Let's try this again. That's a little better. Tau squared U0 for the random intercept. I'm going to put another column over here for residual. So which letter goes with that? If it's not U0, what's the other one? E. Yeah. All right. So let's go over synonyms then. So this model has a random intercept variance that captures what level of variation? 2 or 1? Random intercept. 2. Yes, say it with authority. You guys know this. So I'm going to make a little table here. Level 2. That means residual must be level 1. Yes, indeed. Which one of these is cross-sectional variation and which one is longitudinal? Random intercept is cross-sectional. Writing down cross under that column and longitudinal under residual. Which one of these is mean differences between people variance? That's my random intercept. The random intercept is how far off my intercept is from the grand mean intercept. So that's person mean differences. Person mean diffs under the random intercept column. So that E then has to be variation across time around your mean. Why are you off your mean today? So I'm going to write down off your mean under the residual column. So this model, this compound symmetry, random intercept, two-pile, univariate, repeated measures ANOVA model, all those words go together. It predicts constant variation across time due to two sources, and it predicts constant covariance across time. So that's this off diagonal. Note the same symbol shows up here. That means that the only source of covariance is due to my random intercept. Trying to put that idea into English, what that model on the left says is that people differ from each other in only one way. They differ from each other in their mean, and that is the reason why occasions are correlated from the same person. That's it. So if I were to take this little tau squared U0 symbol and sort of vacuum it out of every single element in this matrix, what would be left is E variance on the diagonal and zeros everywhere else. You will see that literally in a few slides, but that's the idea. It's that the reason that your data were related from occasions from the same person is because of constant mean differences, and that's it. If that is true, then the variance should stay the same across time and the covariance should stay the same across time. Now, when might that not hold? I can think of at least two reasons. If people change differently, right? If people change differently, they spread out over time. So the variance has to change over time. But this week, we're not talking about change data, we're talking about fluctuation data. Do you think that constant covariance is plausible when you have a lot of occasions within a person that are separated by a good distance in time? If I collect data once a day, every day for a year, for instance, some people do that, this model would say that my data are just as related on days 1 and 2 as they are on day 1 and day 365. Nope, probably not. So yeah, even if constant variance over time is plausible, constant covariance over time may not be. On the plus side, though, this picture shows what a compound symmetry pattern would look like for 4 occasions. How many parameters make up this pattern? Unique symbols in the compound symmetry matrix. How many are there? 2. What if I plotted this, what this pattern would look like for 10 occasions? How many symbols would I need? 2. 1,000 occasions? 2. So that's the good side, is that this at least induces a correlation of data that come from the same sampling unit. Even if that correlation isn't constant, you're far better off including something than nothing. So what if this thing doesn't hold? What if your variance differs over time? What if your covariance differs as a function of how far apart in time your occasions are? Well, the only other choice we know is this one over here on the right-hand side. This is the best possible model for the variance you can ever have. Unstructured. Everything gets to be what it wants. There is no pattern. We're not trying to predict what the variance and covariance look like over time using just 2 parameters or just 3 or just 4. No, we're letting them all be what they want. So this example has 4 occasions. That would take 4 different variances and 6 different covariances. What if I had 10 occasions? The formula is number of occasions times number of occasions plus 1 divided by 2. So 10 times 11 is 110 divided by 2 is 55. What if I had 100? A lot, right? Too many, most likely. So yeah. So that unstructured model works well for a limited set of cases. Few occasions, and when everybody is measured on the same schedule. There's a word for that. What word do I use for that idea? Everybody came in when they were supposed to. I heard it. Balanced. Yes, I don't have any candy to throw today, I'm sorry. But you guys didn't want the candy last time anyway, so you'll have to wait until Halloween. Yes, Huey got his Halloween costume while he was away this weekend. You know what he's going to be? A giant cookie. Okay, it's your Halloween. I'll make sure to bring pictures. I'm hoping it's not a poopy cookie. By the way, this is a thing at Hy-Vee in their bakery section. Yes, Teresa's like, what? There are frosted cookies with poop emojis drawn on them. And he thinks it's hysterical. So that's like our bribe right now. If you eat some dinner, you can have a poopy cookie. I know. I'm like, really? Really? But no, if you're a 2-year-old, that is hysterical. So yes, poopy cookie for Halloween. Where was I going? Oh yeah, you guys didn't eat your candy. That's where this started. I'm going to bring in Huey's Halloween candy, most likely, the day after Halloween, because he doesn't like candy either. He doesn't like food as a general strategy. But yes, so multivariate, people have to cooperate, balance data. So if we have people come in off cycle, then that thing can't work. And this is all you know right now. This is the world of choices that are available to you in the world of ANOVA. So we're going to get some new choices today. That's the goal. In order to decide which of these many choices is going to work best for our data, we have to do model comparisons. So just to review this idea a little bit, we're talking about predominantly nested model comparisons where one model is a subset of the other. We haven't had to talk about this yet, and you didn't have to learn about this in most of your other classes because model comparisons involve differences in the model for the means, which predictors to include. You don't have to do likelihood ratio tests for that. You can just stare at the p-values. You can stare at the p-values for each fixed effect univariately or a collection of parameters as a multivariate test, but you don't need model comparisons to do that. For the model for the variance, though, we do have to do likelihood ratio tests. You're not allowed to stare at the p-values for the Wald test. So just to review, your SAS output is going to give you a statistic called -2 log likelihood. Smaller is better. The reason it does that for you is so that you can take the simple difference between models without having to multiply that difference by -2. Twice the difference follows a chi-square distribution, so that they're trying to help you save a step. But smaller is better for -2 log likelihood. So we'll take the difference, the -2 log likelihood from the model with fewer parameters. Because it's simpler, -2 log likelihood will be greater, minus the one from the parameters that the model has more parameters should be lower, so that difference needs to be positive. You take the difference in the number of degrees of freedom, and then you compare that change in log likelihood to a chi-square distribution with that degrees of freedom. So this is the new Excel sheet that I posted using the ANOVA model example from last time, 3B. So here's my E-only model. I had a -2 log likelihood of 9155. I had a total of 7 degrees of freedom because I had 6 means and 1 E-variance. Compared to adding a random intercept, the univariate within-person ANOVA, the compound symmetry model. That deviance was 8353. I added 1 parameter. And then in here, I have it set to calculate the absolute value for the difference. That way you don't have to worry about order. But just remember that the one that has fewer should be first. The one that has more should be second. The difference is 802 on 1 degree of freedom. And then this right here, I know you can't see this very well. Oh, there, made it big. This is an old Excel function called chi-dist. If you try to use this, it might be like, hey, that's from Excel 97. Like, I can't believe you're still using it. Use this one. There's a few other newer chi-square ones, and they don't always give you the right answer. There's different permutations as to what they're giving you back. I know this one works. So you type in chi-dist, you point it to the first argument, which is the -2 log likelihood difference. The second argument is the degrees of freedom difference, and then it returns the exact p-value. So that is where most of my examples, I either have an Excel spreadsheet or I had one at one point in time to do that. Likewise, to compare the two ANOVA models, so what I've been talking about here, these two, compound symmetry versus unstructured. Likewise, I take the univariate -2 log likelihood, same number here, just repeated for convenience. The same -2 log likelihood now from the multivariate model, the difference in the number of parameters, and then that difference is 123. So this is a fairly general procedure that works for a lot of different types of models. You'll notice that for those of you who are used to seeing MLR and M+, you guys did that with me, I know some other classes might. This assumes a scale factor of 1. So you can use those spreadsheets the same and just put in 1 for your scale factor. MLR is not a thing in SAS. Excuse me. All right, so we did that. Yes, I had a couple questions over email about information criteria. The first part of your homework asks you to compute AIC and BIC. I'm not interested in your ability to use a calculator. What I'm interested in is your ability to differentiate how many parameters are in the model based on what I called it, and whether you should be counting all the parameters if you're in ML, or just the variance parameters if you're in REML. So that's what I'm looking for here. N is the number of level 2 units in the BIC formula. That actually varies a bit across programs, but that's what SAS does most of the time. So you can use those to help you figure out the first part of homework 3. So these choices then for alternative covariance structure models, there's basically 2 decisions you have to make. So what we're trying to do is find a pattern for the variance covariance matrix that matches the data as well as possible, spending as few degrees of freedom as possible to do it. Simple but good. That's what we're going for. Question 1, are the variances the same or different? Unfortunately, within this family of models, there's no middle ground. They're all the same or they're all different. So the structures that I'm going to show you will just have a name like, say, topolits, and then there's topolits heterogeneous, where the word heterogeneous at the end refers to whether or not the variances get to be different by occasion. So homogeneous is the default. Second question, covariances. Are they the same across occasions or are they different? And if they're different, what kind of difference? Is there a pattern to it? So compound symmetry is one pattern. There are other patterns that I'm going to show you that are sometimes have the same number of parameters or sometimes have just a few more. Now, when is this not going to be helpful to you? If your occasions are not equally spaced. A lot of these patterns make use of the idea of a time lag, like where lag 1 is 1 distance in time apart, lag 2 is 2 units of time apart, and so on. If your data are not equal interval, then those lags don't actually mean the same thing as you go across occasions. So the patterns that rely on some kind of idea of a lag aren't going to help you if you have that kind of unequal data. Most of these require balanced time. Everybody has to be measured on the same schedule. There are many fewer options if they're not. The good news, though, is that none of these requires complete data because we're using maximum likelihood. And we're staying within the restricted maximum likelihood family because those models are, that estimation, will give you the best variance components in smallest samples. All right, how are we doing? Okay. So we are going to start with the family of what I call R-only models. Almost every other book that I've seen focuses only on those. I've only seen one other book besides mine that talks about the second half of this page. And so I'm covering these more for historical purposes, not because I think they're terribly useful, but because I want you to know what they are. The second half of models that combines these patterns with the random intercept is going to work a lot better. One other caveat. I'm going to remind you about how correlation and covariance go together. Here are the formulas. Now, one of the reasons I like SAS is that you can ask for both the variance-covariance version of the matrix and the correlation version in the same output. SPSS, where's Maddie? SPSS doesn't have the correlation version. So there's just these little things that make it annoying to work with. Otherwise, you'll get the exact same answers back out of SAS and SPSS. What you get on your output, though, is not always clear, and it depends on the way that the model is specified. So these models, if you have homogeneous variance, you tend to get covariances back on your output. Not always, but most of the time. If the model is specified in terms of heterogeneous variances, though, then you get correlations instead. The reason for that is covariance is scale dependent. So if the variances that go into it are different, the covariances are going to change over time as well, even if the same correlation is held. So you really have to know what you're looking at to know what to call it. And I wish this were easier. The only thing that I can do is I've tried to label my examples as best I can, and I've tried to make labels in these things that follow what SAS is going to call it. But this is where it gets a little bit tricky. So I'm using, in quotes here, the labels of what SAS is going to call it for you. One other thing to keep in mind as we go through this is that unstructured is always going to be the best. What we're looking for is something simpler that is not significantly worse. So this is not an exercise in trying to get the model to fit better. It's an exercise in trying to get it simpler, but just as good. If you can't have unstructured because you don't have balanced data or you have too many occasions, then you don't really know what's best. All you can do is keep adding stuff until what you've added doesn't help anymore. So what you know already then, to try and help make this a little less boring, I've decided to go with a show and tell approach. I normally have an analogy based on pants. You'll notice today I am wearing pants just for you guys to help with the show. I had to wear pants last Monday because I had to look like a grown-up because the child language program had external people coming in, so I had to like put on shoes and everything. But no. So let me show you some analogies as to what the models you know already are. I used to call the unstructured sweatpants. And I realized that that expression is a bit dated. Sweatpants, no one calls them that anymore. So I'm going to get up here and show you. The unstructured model fits like these. These are my favorite mom loungewear pants from Kohl's. What would you call these? Because they're not really sweatpants. They're a little more tailored than that. Yoga wear, loungewear. Anyone? What would you call this? It's like cotton, big pockets. You could sleep in it. You could go to the grocery store and no one would look too negatively at you. I need a word. Loungewear? Is athleisure? Is that a thing? Can I say that? Because yeah, I could run in these. So in my defense, these are very mom pants because I need them to chase after a 2-year-old. I have deep pockets to put like dirty Kleenexes and keys and stuff, and big waistband to keep him up whenever I'm bending over to get him. But these are comfortable, right? And just like these pants, unstructured is always going to fit. It's very forgiving. It will let your data be whatever it wants to be, and it will be fine. But unlike, or just like sweatpants, I should say, sweatpants athleisure wear is not appropriate for every situation, right? I did not show up to the external review in athleisure wear, and I generally don't show up to teach in athleisure wear. So just as unstructured would fit best, it's not always appropriate. If you don't have balanced data, if you've got a whole lot of occasions, it's not going to suit you well. But the good news is that, much like my loungewear, unstructured will always fit. If I ever grow out of these pants, Lord help me, right? It's a bad day if I can't fit into these. Pregnancy accepted, right? Those are beyond your control. I don't have my next gimmick because I can't wear them, but skinny jeans is like compound symmetry on the other side, right? They're strict. They go all the way down and everything has to stay the same or they don't look good. I don't look good in skinny jeans. I will never look good in skinny jeans, and some of you will. They're tough, they're unforgiving. It's not that they're wrong, it's just that they're not for everyone, right? Some people, like myself, should never wear skinny jeans. And compound symmetry is it's very unforgiving as a model. You have to have everything exactly the same over time, and parallel growth and equal covariance, and it's not realistic. Now, to make it slightly better, getting back down here to go change my slides, we can make it slightly more forgiving by introducing different variances across time, and that makes it heterogeneous variance version of compound symmetry, where on the diagonal we have different variances instead of the same. So this pattern is more forgiving in that it allows your variance to change over time, but it still says that your correlation is the same over time. There are very few cases in which I've seen this model work for data, but what it will return to you is something called a variance and then a number in parentheses. That's going to be the total variance at each occasion, and then some parameters that's called CSH. That stands for compound symmetry heterogeneous, and it is the correlation that is constant over time. So the end result is that if you take that correlation that's held constant everywhere and multiply it by what it thinks the two variances are for that pair of occasions, then you get a covariance that changes over time, even if the correlation is the same. I don't find a whole lot of use for that one. Next one, autoregressive. And this is the one that I had to wear my pants for today. All right. So back in the 80s, which most of you missed, there was a fashion trend that I was part of in elementary school when it came out, which was peg rolling jeans. Do you know what this is? Quiz, see, this is why I knew I would have to demonstrate. See, you take your jeans, which usually we're kind of straight leg jeans. You fold it over, and then you give yourself like high water pants on purpose. Okay? Can you see? Ooh, I'm like the Karate Kid up here. So we all walked around like this for reasons that are still unclear. This was required. So I even had jeans that had like these little zippers right here, and I would still peg roll even though the zipper would like dig into my skin and make me bleed, because like that's just, it was required. So we all walked around like this. I don't understand why, but I can tell you what's wrong with this. This as a look, generally speaking, it comes from Stacy and Clinton. Okay, people, a few smiles. What Not to Wear was a pivotal show in my 20s and some of my 30s. I loved that show. But Stacy and Clinton would talk about like tight, ankle jeans. What's wrong with tight ankle jeans as a look? Can anyone tell me? What was their problem with it? Because you get people on the show with like mom jeans. It was like, the big high-waisted with the tight ankles. They look very bad on most people because they make your ass look huge. Because it's like everything narrows down, so everything looks that much wider on the top, right? That is the problem with the autoregressive structure too. It gets too narrow at the bottom. The way that this thing works is that it estimates one correlation and for occasions that are 1 unit in time, it says that's how correlated they should be. So for instance, if I had an autoregressive correlation of 0.8, it would say time 1 and time 2 are correlated 0.8, time 2 and time 3 are correlated 0.8, time 3 and time 4 are correlated 0.8. That's the R with a 1 in the superscript column up here. So this only makes sense if your occasions are equal interval. That's one problem. But then what it says should happen after that is that the correlation dies down as an exponential function of time. So it goes from R to R squared. So occasions 1 and 3 and occasions 2 and 4 are supposed to be correlated R squared, which would be only 0.64 in my example. And occasions 1 and 4 would be correlated R 0.8 cubed, which is, any math people? Can someone find out? What's 0.8 cubed? Anyone? Not a trick. I just don't have like, multiplication tables in my head. What's 8 cubed? 0.8 cubed? 0.51. Can you guess what it would be if I had occasions 1 and 5, 4 units apart? R to the 4th. How about 5 units apart? R to the 5th. And so on. So, much like the tiny ankle jeans, it gets too small too fast. That's the problem with this structure. When I've seen it, I've never seen it fit longitudinal data ever, like ever, because it thinks the correlation dies off almost immediately. And data from the same people tend to be related even if it's very far apart in time. There's always some minimal correlation there that's present. So this model is overly harsh, it's overly strict in saying that the correlation gets too small at the bottom, just like my pants. Now I have to unroll this. Oh, it doesn't know and it doesn't care. It has to be equal interval or this makes no sense. However, there is a variant of this that you can do for unbalanced data. It's called a spatial power structure. I have that coming up in here. It's only in SAS though that I've seen. So yeah, just like compound symmetry had a heterogeneous version, this one has a heterogeneous version too. It's ARH. 1. Now I make a point about saying how infrequently this model fits. So I got to draw another picture here to make you think about how this applies to other contexts. Have any of you seen path models for longitudinal data that looks something like this? A box for time 1 predicts a box for time 2, predicts a box for time 3, and so on? You seen this before? A lot of the time, they'll take the parameters between occasions and they'll constrain it to be the same. They call that the stability coefficient. Guess what this is, folks? This is that. This is an AR1 model. It says that occasions 1 unit apart are correlated the same number. By the rules of path model algebra, I can take this path times that path to get to what the correlation is between time 1 and time 3. That's r squared. And if I do it again to get out to time 4, that's r cubed, and so on. So this is something that we'll probably get to in a lot more detail next semester, at least I hope to. But point being, for the same reasons that AR1 structure rarely fits longitudinal data when used by itself, the correlation gets too small too fast, this version of path models is inadequate. I will show you how to fix it if any of you are working on data that look like this. But you should learn that this is not a good strategy. Neither is peg rolling, as it were. Last one, and then we'll look at our example, TOEPlets. I keep calling it TOEPlets for some reason, but that's not how it's said. It's TOEPlets. This is also based on a lag, but it's not as strict. I would call this maybe like straight leg gene or boot cut, something that's like still restrictive but a little bit more forgiving than the tapered gene. It has a homogeneous version and a heterogeneous version. And in the first off diagonal is one parameter for covariance. In the second off diagonal is another, and another, and another, and another. So it allows different covariances by time lag, but they're not tied together. So autoregressive is one correlation that's supposed to decay by squared and cubed and fourth. This is as many separate covariances as you have time lag. So this one would be 3 different numbers estimated in the off diagonal. Those covariances then become correlations down here with the same exact pattern. You see the n in parentheses here? That's only available in SAS, by the way. The default without the n is as many parameters as it takes to fill up the matrix. But this is going to be our friend later on once we get to the random intercept versions of these models. What n means is the number of, say, diagonals is not quite the right word. 1, 2, 3, 4. I'm going to say diagonals. Like this is the first diagonal, and this is the second, and the third, and the fourth. That's what that refers to. You can have fewer than that estimated, but you can't have more. So we'll see reduced n models coming up later. So those are our patterns. Unstructured, athleisure wear. Always fits, not always appropriate. Compound symmetry, skinny jeans. Very restrictive, doesn't work for everybody. AR1, tapered jeans. Gets too small at the bottom. Correlations do not decay that quickly within persons. and topolets, which I'm going to go with maybe, like I said, a straight leg or boot cut, has the same pattern of differing covariances across time, but not necessarily decreasing. It could actually go out instead of in, just like some boot cut genes go out instead of in. So these are some new choices. If we go back to this picture, so I have compound symmetry on the left. That's the homogeneous version. If I test that against compound symmetry heterogeneous, how many more parameters have I added? I would love to. So if I have compound symmetry, right? Now we said earlier, no matter how many occasions, how many parameters is that? 2, yes. So now, if I go to compound symmetry heterogeneous, which refers to letting the variances be different across time, how many more parameters have I added? One, so each time gets its own. So if I have 4 total times, how many have I added? Charlie, you're waving? How many? 3? Yep. I already have 1 variance, so I just need 3 more to get to the 4 so that each gets its own. So if I do a significance test to compare the fit of these 2 models, and it's significant, what would that mean? CSH is better, not better, worse, or not worse? Have I added? Better, yes. If it's significant, then it's better, yes. Now let's say I'm in a situation in which I can also test unstructured. How many unique terms are in that unstructured matrix for 4 occasions? Four variances. How many unique covariances? 6, yeah. So that one has 10. Everything is nested and unstructured. So if I compare CSH to unstructured, I'm up to 5 parameters in it. I'm up to 10 for unstructured. If I do a significance test and it comes up significant, what does that mean? Which fits better? Unstructured. What if it comes up non-significant? Not worse. Exactly. So it depends on your perspective what you're going for. The purpose of testing against unstructured is always worse or not worse, because nothing can fit better than unstructured. It wins. Nothing is more comfortable than athleisure wear. It wins. So this will be the process of trying to figure out, is it not worse than unstructured where we have that option? And if we don't have that option, how does it compare to CS? Now what about AR1? Let's look at that one again. Yeah. How many parameters is AR1? Feel free to read from the slide. 2. What if I had 10 occasions? 2. Yeah. So that means it is not nested or non-nested relative to CS, it has the same number of parameters. So it can't be nested if the degrees of freedom are the same. If I test AR1 against ARH1, how many parameters have I added? Heterogeneous variances for 4 occasions. 3 again, yep. So it's the same logic. If you're testing whether or not variances need to be different or the same, it's always number of occasions minus 1 for the differences in the number of parameters. I can do the same test against unstructured to see if that is good enough as well. Last but not least, TOEPlets. How many parameters in this one? N, right? It says right here, N. That's how many. How many is N? N means number of occasions. So if I have a 4x4 matrix, that means I have 4 occasions. 4, yeah. It's 1 variance and 3 different covariances, 1 for each time lag. And put that one up here. So this is one that gets more parameters the more occasions you have. Right now we're at 4. What if I want to test the heterogeneous version of that? TOEPH. How many would I add? 3, yes. Up to 7. Then 7 versus 10 would be the test of whether or not that's good enough. So these are some more choices. They're somewhere in between. Everything has to be the same over time, and everything gets to be what it wants over time. Questions? Do you want to see an example? Why not, right? Yeah, still streaming. That's good. Just got to check. So these data, being back at KU allows some extra relevance to some of my stories. These data are from a dissertation of a former KU clinical student. When I was a graduate student here, I worked as part of her lab as a data analyst, and I ended up helping her analyze these data. And this is a study examining changes in psoriasis severity, differences in psoriasis severity as a function of stress and as a function of personality variables like coping and forgiveness and stuff like that. So this student went into her dissertation proposal meeting with this lovely little cross-sectional study where she was going to measure individual differences in all of these things. And she had access to a dermatology clinic where people who had psoriasis went, and she was going to measure their psoriasis and see if stress and psoriasis were related differently in people who were better copers and that kind of stuff. And 2 hours later, she came out of her dissertation proposal meeting with a longitudinal study that her committee had helpfully designed for her. This is the result. This type of plot, you could call it a plot of individual trajectories. It's also known as a spaghetti plot because it looks like if you had a handful of wet spaghetti and you threw it at a wall, like that's about what you get. So the mean line here, this black line conveys the means over time. This is a 7-week study. I'm not including the first week for reasons that will be more relevant later on, but 7 weeks of data, where each week she sent questionnaires by mail as to how bad their psoriasis was that week and what kind of stressful events they had happen to them. So this example is real data. That's why I don't have the data and the output available for you, but you can see what happens. I have a little bit on the proc mix stuff here, just in case you want to get a refresher on what the commands give. So let's start with the simplest possible model for pedagogical purposes for review here that says there's no covariance over time between occasions. That's my E-only model. So my proc mixed code, sub ID stands for subject ID. That's my level 2 identifier for person. Week is my level 1 ID for which occasion is which. Severity is my outcome. My repeated statement has week so that it will align the columns of my variance covariance matrix appropriately. And the structure here is VC. Remember what that stands for? Variance components. This is a model that says occasions from the same person have nothing to do with each other. It's the simplest possible model that we could have for the variance. It's a regression model. Taking that idea and expressing it in a form that looks like a matrix gives you this. This is our friend, the R matrix. Note the number in it. It's all the same. Coincidence or not? We told it that. This model says the variance is the same across everything, all people, all times. And the big blank spots where the covariances should be and the big blank spots where the correlation should be tells you what? What kind of correlation over time does this model predict? Blank. Say it, Amy. None. Yeah. So this is as bad as it gets. So this -2 log likelihood, if this is the worst possible model ever, is that the highest number we're going to see or the lowest? Highest. Smaller is better. This is confusing, and this is a question on your homework. Log likelihood and -2 log likelihood are inversely related because of the minus sign. Likelihood, higher is better. -2, smaller is better. So that one is unrealistic. Let's see about the compound symmetry model. How much of our variance is level 2 versus level 1? Here's my friend CS in the code. So this is a model you've seen before. See if I can get this show up at the same time. So this is my compound symmetry model. It has 2 parameters, even though there's 7 occasions. It says each occasion's variance is part U0, that's my compound symmetry parameter, which is 0.68, and part E, which is my residual variance, which is 0.13. If you sum those together, you get what's on the diagonal up above, 0.81. That's the total variance across time, equal across time. The off diagonal up above now has some numbers in it. The same number. This is the model that says the only reason that occasions from the same person are correlated is person mean differences, is random intercept variance. And so that's why random intercept variance is showing up in that off diagonal. If I take that covariance and translate it into a correlation, that correlation is 0.84. That correlation of 0.84 has a special name, right? That's the ICC. So 84% of the variance in psoriasis severity is level 1 or level 2? 2. is between persons or within persons? Between. Is cross-sectional or longitudinal? Cross-sectional. So let's visit this poor graduate student now. That means her committee wasted 84% of her time. 84% of the variance she could have had with her original one occasion study. Thanks, guys. But then I wouldn't have this lovely example, so I win. And she wrote it up and turned it in, so she won too. So I can do a likelihood ratio test to compare my previous E-only model that had one parameter to this version that has two parameters. And that is exactly what's done for me in SAS. So in this one case, SAS will do it for you, but not more generally than that. The difference in -2 log likelihood is 950. So yeah, adding a random intercept made the model fit better. So yeah, a correlation of 0.84 is bigger than 0. So let's go with the unstructured athleisure wear and see what it thinks the best possible model is going to look like. This is an instance in which observations were collected 1 week apart. Everybody got collected at the same schedule, so it's balanced, so I can do this. So here's our UN. For 7 occasions, that requires 28 parameters. And here it is. So I've highlighted the variances on the diagonal. Do those look the same or different to you? Yeah, some of them look different. Some of them kind of look the same. Different like randomly or different in a pattern? Okay, yeah, it's kind of random, right? Yeah. So this ain't growth data. Do you know how else I know this ain't growth data? This picture. I feel bad for this person. Their psoriasis went away, and then it got really bad again. Or more likely, week 4, they're like, screw it, I'm not going to fill this out, but I'll mail it back to you since I get money for doing it. Just a hypothesis. So yeah, different variances maybe in a random pattern. How about the correlations over time? Do they look the same or different? Kind of different. Different in a pattern or different random? Pattern-ish, I'd say. Generally, the ones that are closer together, occasions closer together, look a little higher, but not always. Now, I do want to point out something. Check out, the last one here. Between row 7, column 1, that's week 2 and week 8 of this study. The furthest apart in time is still 0.8. So I know right from that, AR1 is not going to fit. AR1 would predict a correlation by then that would be R to the 7th, which would be probably near 0. So here's my -2 log likelihood. Is this number the biggest I'm going to see or the smallest I'm going to see? Smallest. This is the best. However, what about BIC? For instance, this model that is the best model ever, BIC is 1028, whereas the 2-parameter compound symmetry model, it's 1059. Well, BIC is still smaller for unstructured, but not by nearly as big a margin. BIC and AIC adjust for the number of parameters. So BIC in particular, because it's number of parameters and sample size, it really has to get better before BIC is happier with it. So let's see this not work as predicted. Charlie. Great question. Two different things. So this incredibly complex model, 28 parameters basically, to uniquely identify every possible variance and covariance, still says nothing about growth. This is the model for the variance, not the model for the means. In the model for the means, fixed effects, what do I have? Nothing. It's empty. So this is not a story about growth. On average, the mean level of psoriasis does not differ by week. 17 or 16% of the variance is within persons over time. The question is about the pattern of variance and covariance over time. Growth is not a reason why it's non-constant. Fluctuation is. So this is as good as it gets. But 28 is a whole lot for something that looks like it could be boiled down into a simpler pattern. But it doesn't have to do with growth. It has to do with fluctuation. Now, the fact that the ICC is so high tells me that any pattern that predicts correlations to go down a lot over time is probably not going to hold. There's a constant correlation, even at the highest last occasion, of 0.8. So this is actually foreshadowing the solution that I'm going to end up with, which is combining a random intercept plus some kind of pattern. The 0.8 tells me that I need something constant. There are constant mean differences, but I'm also going to need something else because that correlation does vary across time. So does that help at all? Okay. So here's my AR1 model. You type equals AR1 with the 1 in parentheses. So let's look at the pattern that it predicts. This is the homogeneous variance version, so it's constraining the variance to be the same across time. So it's saying the variance at each occasion is 0.7999. This is where the job security portion of the program starts to show up, by the way. Out here with Proc Lesa, I have labeled this shit for you. Because guess what SAS calls this? Residual. This is not residual variance, folks, because we have not differentiated random intercept variance from residual variance. That's not how this model works. It doesn't work by dividing into levels. Everything stays together, and instead, it induces a correlation through an autocorrelation parameter rather than a random intercept. So you can see what happens then in the R-core matrix right here. The first off diagonal is weeks 1 unit apart, so week 1 with week 2, 2 and 3, and so forth. That autocorrelation is what the correlation is predicted to be. That autocorrelation squared holds then for the next set of off diagonals. That correlation cubed is the next one. 4th, 5th, and 6th. No one's ever told me what to call that, so I just made it up. This is R to the 6 down here. So this predicts that the highest lag, the furthest distance in time, is supposed to be correlated only 0.5, whereas in the data it's 0.8. So this isn't going to fit well. How well does it not fit? Well, here's my fit statistics. It's significantly worse than the unstructured model. I can't compare it to compound symmetry because it's a 2-parameter model, but I can look at AIC and BIC. It likes AR1 a little bit better than compound symmetry, it looks like. Along with this example, by the way, I have posted an Excel sheet that has all of these models, the number of parameters in their variance model, and their -2 log likelihood in AIC and BIC. I then have a series of likelihood ratio tests comparing them against each other. So I did this in Chapter 4 for a different set of data, and I'm doing it again here for this set of data so that you'll have 2 different examples to go through to try and see how these things relate to each other. So no, it doesn't like this one. I didn't test AR1H because the correlation part didn't fit well, so there's no point saying if it gets better with heterogeneous variances. But I did do TOEPlets. So TOEP7, if you don't put anything in parentheses, it automatically gives you the highest order TOEPlets it can, which is one parameter per occasion. This is another homogeneous variance model. And now this is specified in terms of different covariances on each off diagonal. So here's the first one, 0.72, 0.69, 0.65, 0.63, 0.63, 0.65. And those parameters then for those covariances are all listed right here. So this model is more reasonable than AR1 because it doesn't restrict the correlation to decay based on one number. It gives a different relationship for every possible time lag. Yeah. And if I compare this one to unstructured, P equals 0.047. Should I say yay or oh? Yeah, there you go. Yes, alpha 0.01, yay! Yeah, so this is almost not worse than the best model possible. Let's see if I can make it better by doing heterogeneous variances. Try the TOEPh. Now the off-diagonal elements are specified in terms of correlation, as you can see here. And there's my 7 different variances. I added 6 new terms to allow differences in variance. That didn't actually help. And so that drags down my overall fit comparison, so it definitely is worse than unstructured. So it looks like then this is where the story would end with the traditional approach to these patterns, TOEPlets. Next time, I'm going to show you what I think is a more useful approach and also more generalizable to more kinds of fluctuation data. So stay tuned for that. But now, Teresa, you came up after class and you're like, what the hell is this like autoregressive heterogeneous thing? You know now, right? Okay, so you can do more of your homework than you could before. Hooray. All right, that's it, folks. I shall see you next time for more show and tell and stories of what happened to my pants on my initial job interviews. True stories. You heard it here. Office hours start now.